how dust in astrophysics possibly could figure into developments in modern astrophysics. It sounds like an extremely dull subject. So I'll try to convince you that it is not a dull subject. It is actually very important in astrophysics. And when you combine it with the fact that the speed of light is finite, the presence of dust in the universe allows us to do a number of very unusual things. So I'll hope to be able to show some of those to you. Here's a little animation. There we go. So I called the title Dust in Astrophysics as a Nuisance and an Opportunity. And I would like to stress, before we go any further, that work that I'll show and things that I've done over the last year or so, I've done in collaboration with a big group of undergraduate students who are all listed down here. I have to say, yes, these are trying times and these are strange situations. But for our particular profession, it turns out there's a lot of things you can do on the web. And the students have been coming in and have been asking for research projects by the dozen, and we've been able to accommodate a lot of them. And we've been able to do a lot of productive work over the summer. All we need is really a video link and a laptop, it turns out, for a lot of what we want to do. So as Mike said earlier, science is going to be the way out of the current situation. And for that reason alone, it is important. I would also say it could contribute to our mood because in my experience, good science is always fun. And it's actually something you can do yourself. So with these students, I've had a lot of fun this summer. So I want to show you some of the fun things we've been doing. So I'll say a few things about the importance the importance of dust in astrophysics in general. Then I'll show you why dust is a nuisance in many situations, how it makes it difficult for us to do measurements of cosmic distances without systematic biases. And that, of course, is a serious issue. And then I'll talk about dust as an opportunity. We can actually see the past. We can look at things that have already happened and for which our opportunity to see the event when it first happened has already passed. But as I'll show you, we can use the fact that there's dust in our galaxy to see things that we otherwise would not be able to see. And we can also use it to locate unusual objects. So I'll illustrate this with something that I'm personally interested in. I would like to find the counterparts to gravitational wave sources, and I'll tell you why that is important, and I'll maybe try to indicate why that is currently not feasible, and how this idea that we've been developing can actually contribute to this, and finding the first counterpart to a gravitational wave source. So many of you probably live in the Hudson Valley, like I do, and so I thought we'd start with a picture of the Milky Way over the Hudson Valley over here. And here's the Milky Way right here. You can actually see that it's sticking straight up, right? You probably know what this means. We now know that the Milky Way is a huge collection of stars in the shape of a pancake with a little bit of a bulge at the center. The sun is somewhere halfway out in this pancake. The pancake is actually quite thin. And in the plane of the pancake is all sorts of stuff. There's lots of stars, and these are the stars that are very, very far away. So we see them as bright patches, basically, and not the individual stars. Over here, you can actually see the stars that are closer in, because the pancake, though thin, is not infinitely thin. And so these are the stars that sit in our local piece of the pancake, and we see them in all directions. Now, if we were able to look at this from a distance, which we can't, but we can look at other galaxies that we believe look very much like our own, then we see something that looks like this. And so here we see the disk of a galaxy that probably looks much like our own. It has a spiral shape. It is a pancake shape. It has a bit of a bulge at the center. This is an image of NGC 5128, which is the host to the radio source Centaurus A. It's an image taken by the Space Telescope, and the object is about 10 million light years away. And as you can see, there's all these stars over here, and there's light back here. And then you see this dark material floating around over here. That's actually dust. And even though in astronomy we usually refer to this material as dust, it's probably better to think of it as soot, because it is little carbon and silicon bearing particles with sizes that are actually sort of small compared to the dust in your house. If the dust in your house had sizes, dust particle sizes that are comparable to the dust in interstellar space, then trying to use a vacuum cleaner would probably be quite ineffective, because the stuff will cling to everything. So there's dust in the galaxy. There's dust everywhere, probably in our own galaxy. If I go back, you can actually see these dark spots over here in the middle of the pancake. And those are not locations where there are no stars. Those are locations where the stars are obscured by clouds of dust in the plane of the pancake that make it impossible for us to see very far. So now, dust is important in astrophysics for a number of different reasons. So I'm basically now kicking to the curb 16 separate talks, but I picked out one particular topic that I would highlight that is quite spectacular. In galaxies that are newly forming stars, there's usually lots and lots of dust. It's not being blown out, hasn't been removed yet or been destroyed yet. And as stars are formed, many massive stars form. Massive stars are luminous and they're very blue and hot and produce lots of UV radiation. And this UV light heats the interstellar gas, and the interstellar gas warms up to high temperatures. And the interstellar gas can only cool again and stay in the galaxy because it can actually re-radiate the energy that it absorbs, the ultraviolet radiation that it absorbs from the massive stars, because there's dust embedded in the gas. The dust gets heated, and the dust can re-radiate a lot of this ultraviolet light, the energy carried by the ultraviolet light in microwave radiation. So star-forming galaxies that are currently making stars at a rapid clip, as they have been doing in the past when the first galaxies formed, gives rise to very bright high-frequency radio or microwave radiation, and that's from the heated dust. So here's a picture that shows the sky in high-frequency radio radiation, and somewhere in this little square, if you can see my little cursor, in this square over here is buried an object that's been magnified out here. This object here is a star-forming galaxy. It has the unimaginative name HFLS3, and you can see in the high-frequency radio radiation of warm dust that it is a bright object. This thing stands out, and it's at a distance that's so far away that the universe was less than 1 billion years old when this light was made. So when you look at the sky at these high-frequency radio waves, you find galaxies that produce lots and lots of radiation. You can see them across the entire universe, and they're visible because their dust radiates a lot of the energy that was produced by the massive stars. For that reason alone, dust is an important thing. But that's not what we'll talk about today. So we'll go into dust as a nuisance for a start, because we'll have the dessert after the main dish then. So dust as a nuisance. So this is maybe how you've heard about dust in astrophysics, because it obscures our view of the universe in a fatal way in some circumstances. So there is a lot of dust in interstellar space. Interstellar space in most galaxies like our own is extremely smoggy, so to say. And if you were to take some of the interstellar medium gas, which has very, very, very low pressure, very, very low density, and you compressed it to the density of the Earth's atmosphere, then you would not be able to see through it beyond about 1 meter, right? So this makes Los Angeles look like clear skies. You would not be able to see beyond 1 meter. So a fair fraction of the mass of the material in between the stars is gas, but a lot of it is also dust. The material, the soot is really everywhere, and it heavily obscures our view of our surroundings. And this is illustrated separately in this graph right here. So here are 4 views of the plane of the galaxy looking towards the center of the galaxy. So the plane of the galaxy is oriented along these horizontal directions at 4 different wavelengths of radiation. So at the bottom is a picture of the plane of the galaxy in visual light, to which your eye is sensitive. And you can see that the center of the galaxy is located over here, and there's nothing to be seen right there, right? There's no feature that stands out other than this little circle, which of course is not visible in the sky. So the galactic center at the wavelengths of light to which your eye is sensitive is utterly invisible. It is hidden behind huge amounts of dust, and you cannot really see it. If there were no dust, then it would be bright enough that it might compete with the brightest stars in the sky, but it's totally obscured. You can't see it. You can see there's a few other galaxies that have been indicated over here. M8 is, I believe, an external galaxy with NGC 6357. So if you go to wavelengths of, if you go to infrared wavelengths, which is heat radiation, longer wavelengths than the wavelengths of visual light, and something appears to be hotter than its surroundings over here. The galactic center is starting to peak out, and at long wavelength infrared light, you can actually start to see right here, there's the brightness of all the material that produces heat radiation in the center of the galaxy. And if you go to microwave radiation, then you can actually see through most of the dust, and you can see the center of the galaxy. So, so this is dust is nuisance, and dust does two pernicious things to light. Light is the primary material that astronomers work with, of course. So dust absorbs and dust scatters light. If there is a dust particle over here in blue, light comes in, indicated by this squiggly line. It hits the dust particle. Two things can happen. The light can be absorbed. It's really gone afterwards. So there's the light, and that's it. The dust particle stops the light short. And you can also have the light hitting the dust particles. And instead of traveling in the original direction, the light is still there, but it's now traveling in a different direction. So it has been scattered just like a billiard ball in a different direction. So now, either way, of course, if you're looking at light propagating through the interstellar gas, and a fair fraction of the light propagating through the interstellar material hits dust particles, then the presence of the dust will dim distant objects. Whether the light is absorbed or scattered, either way, it's lost to the beam of light that was propagating towards us. So distant objects are going to appear systematically dimmer than they should be if there was no dust. And so the presence of the dust systematically biases all our efforts at trying to determine distances in the universe. And you can imagine that that is a serious problem. There are ways of finding out how much dust there is along a given line of sight. If you can see the background objects, the dust not only scatters light and absorbs light, or I should say it scatters light and it absorbs light. In the case of scattering, the scattering is actually more efficient for blue light than for red light. And so what will happen to the colors of stars behind clouds of dust is that the colors of stars will systematically shift towards the red. And so if we see stars, and a detailed study of the light of the stars indicates that they are of a particular type, and we compare the color that they appear to be with the particular type that they should be, then you find that the objects that are close to us, when there's no dust obscuration, have systematically bluer colors than the very distant ones. And so if you can quantify this amount of reddening, as astronomers call it, you can say something about the amount of light that has been lost. But in either case, this is not a good situation to be in, of course, to have a systematic bias of unknown magnitude in principle on all your distance measurements. And so I'll just indicate one example of how pernicious this effect may be. So here's, you may have heard, you probably have heard about our recent findings that the expansion of the universe, the rate of expansion of the universe is changing. And about 20 years ago, it was found that the sense in which the rate of expansion appears to be changing is the opposite of what people had expected. So the expectation that we all had was, as the universe expands, and it does expand, we know that, then the presence of matter and energy in the universe will tend to slow the expansion rate. And this is completely analogous to when you take an object at the surface of the Earth and you throw it up vertically. As it goes up, if you throw it very fast, it might actually leave over time, but it will be slowing down on its way out. If you don't throw it fast enough, it may go up to a fixed distance from the Earth, turn around and come back to you. So that's what gravity does, and that's what gravity would do to the entire universe. It does do that to the entire universe. The expectation was that we would see, if we looked in the past, the size of the universe increase, and we would also see that that there would be a change in the rate of increase, in the sense that the expansion of the universe was slowly slowing down, being held back by gravity. And as you may know, in the late years of the 20th century, we found that, in fact, currently the opposite is true. The expansion rate is increasing. And so if I may use an auditory analog, which is quite effective, I found if you imagine that we can make sounds to represent what happens to the expansion of the universe, it expands from the Big Bang, and people thought it was going to be expanding and slowly slowing down. But what we found is, in fact, it does. Currently, the expansion rate is increasing again, but we do know that it was slowing down in the past, as we expect. So this is what's meant by the cosmic acceleration that you may have heard about. Now, our attempts to lay out the expansion history of the universe are all predicated on the idea that there are objects in the universe for which we know how much light they produce per unit time, what their absolute luminosity is. And if we combine that with the measurement of the size of the universe at the time, at early times when we see these objects, so we can determine the distance to them, we know how long the light that we now see has been traveling. And if we can also measure the state of expansion of the universe at the time that the light left, which we can do from comparison, careful comparison of the wavelengths of the light that we actually see, then you can plot a expansion history of the universe. And I'm not going to try to explain all of this in detail, but our ability to tell that the current expansion rate is increasing again is hinging on our ability to tell true brightnesses of objects to better than 10%. So if there's a systematic bias on these distance measurements, a systematic bias on the light travel time towards distant objects, then we're going to find results that are biased in a certain way. And so if not all the light that a distant object produces reaches us, that might actually masquerade a situation in which it looks as if the expansion of the universe is rapidly increasing. The expansion rate is increasing. So in order to tell the true brightness of objects to better than 10%, to be confident that there's no more than 10%, or preferably much less than 10% of the light been lost to absorption and scattering by dust in the intergalactic space, then there must be fewer than 1 dust grain per 10 to the 20 cubic centimeters. And so that is 1 dust grain in a cube 30 miles on the side. And it turns out that people who study the formation of stars and the evolution of galaxies in the early universe predict that there should easily be this amount of dust in intergalactic space. And so it is perfectly conceivable that there is a systematic bias on our distance measurements to distant objects, which we use to try to lay out the expansion history of the universe, that is systematically biased to the point that it is of an order of magnitude that in principle is comparable to the effect that now looks to us like the universe's expansion rate is increasing. So now we've been able to put limits on these small amounts of dust, because 1 dust grain in a cube per 30, that's 30 miles on the side is a very, very small amount of dust, of course, but the distances in the universe are enormous. And so this kind of thing builds up. There are ways to detect these small amounts of dust, and we've looked at some of those, but that's something for another talk. But dust is a serious problem in trying to do systematic distance measurements, and this affects such things as are currently at the forefront of astrophysical research, as, for instance, trying to find out why the universe's expansion seems to be increasing. The rate of expansion seems to be increasing. Now, being an optimist by nature, I guess, and my curiosity is such that rather than thinking about nuisances, I actually like thinking about opportunities. And so it turns out the presence of dust in our galaxy and other galaxies offers a series of totally crazy opportunities for doing observations that you wouldn't think are possible. And so I'll try to explain how those work. So now we're talking about dust as opportunity. And I'll remind you of the simple idea that when dust or anything scatters light, it will make a halo. So if you look at a distant light source and the light comes to you through a medium that can scatter light, it can change the direction in which photons of light were traveling, then we'll see the direct light source, but we'll also see a halo around it. This is this light that was actually taken off in a slightly different direction. It got scattered off of material in between us and the light source and ended up traveling towards us. And so we see surrounding a light source over here, we'll see a halo of light. All of this light, if there was no dust, would be traveling away in a different direction. It would never hit us. But because there's material in between the light source and us, the light travels to a certain place, gets scattered, and then moves in our direction. So we see light coming from locations that surround the direct light source. All the scattered light will be in a halo. And to illustrate this, I found this image on the web. I got permission from the author to show this. This is the Walmart parking lot in a suburb of Toronto in Ontario, Canada. And it nicely illustrates the point I wanted to make. You see all these direct light sources over here, and they all have halos around them. And that is from, in this case, the fog. Little water droplets will do the same thing. They will scatter light. So now let's take a simple diagram to illustrate the situation in more quantitative detail. If there is a source of light over here, and we are over here, then light can travel from the source of the light directly to us. So we'll call that the direct light. There's also light that leaves the source that's going off in this direction, and it would go and keep going in this direction but it hits a scattering particle over here, and some of that light actually gets scattered in our direction. So in addition to the direct light from the source, we'll also see light that went this way, gets scattered, and then comes to us. And as you can see from the simple geometry of the diagram, the path traveled by the light that was scattered, the light that comes in the halo, is actually longer than the path that's traveled by the direct light, right? So r sub s, which is this distance over here, plus r sub 0, which is this distance over here, is longer than this distance d over here. And so, in principle, light that left two photons, one of them that traveled this way and one of them that traveled through this path, the one that travels through this path will actually arrive later. There's going to be a light travel delay. And now this is something you're not familiar with, because in your living room, you know, when you shut down the reading light, that basically obscures, the room is dark all in one go. You switch on the light travels so fast, the entire room lights up instantaneously, right? But the distances in astronomy are huge. Our own galaxy is huge. And so these light travel distances can actually amount to serious amounts of time difference. So if the angles are small, if this angle over here is, you know, of order a degree or a few degrees or so, then you can show that the extra light travel time between this distance and these distances over here is characteristically of order this light travel time over here, d over c, times the square of this angle over here. And the angle is expressed in radians. So if that angle is of order a degree, you may know that, in fact, in that case, the angle in radians is of order 10 to the minus 2. When you square that, that becomes 10 to the minus 4. So for the situations we're interested in, this extra time delay is the time it took the light to travel directly to us times a small number of order 10 to the minus 4 or so. So now the diameter of the galaxy is of order 60,000 light years, right? We know how far away from the center of the galaxy we are. And so if the direct light travel time can be as long as 60,000 light years, then these extra light travel delays can add up for an angle of order a degree, right? This angle over here, angles of order a degree, the extra light travel time can easily be of order a decade. And so if a source near the center of the galaxy went with a big increase in brightness, a flash of light, we would see the flash of light, and then about 10 years later, we would also see the flash of light occurring in the light that was scattered. We'll see the halo light up later. Does that make sense? And the later here is of order years later. For angles that are a couple of degrees to up to maybe 10 degrees or so, you see that this number, a decade, can be as short as a year. It can also go up to centuries if theta is large enough, the scattering angle is large enough. Then this path length difference with this travel time over here can add up to something like centuries. Okay, now we can do the following. Okay, so let's take an event that was definitely a flash of light. Let's look at Tycho supernova. The Danish astronomer Tycho in 1572 reported seeing a new star in the sky, a nova, stellar nova. We now would call it a supernova to distinguish it from more wimpish nova-like explosions. And Tycho saw this in November of 1572. So in whatever the light travel time is towards the Earth, in 1572, the signal from this increase in brightness, the supernova explosion, reached us. Right now, we now know that that is about 9,000 light years away. We know that the explosion that gave rise to the supernova is about 9,000 light years away. And so now we can go and see if there are any paths, right, for what angle, and we can fiddle with the location of this top of the triangle a little bit. Suppose there are dust clouds all around here. What is the path that would actually take 400 and how many years did I figure? 448 years longer than the direct path, because that will be light. Here's the light that reached us right away. Here, and this is the light that reached us in 1572 when Tycho saw it. This would be light. If it takes 448 years longer, that will reach us in 2020. We would see it this year. And it turns out for an angle of order about 10 degrees or so, that is definitely a possibility. So just for definiteness, because there's a definitely very pleasing aesthetic aspect to being an astronomer and doing astronomical observations, I show a picture of Tycho supernova remnant. I also found a picture of the book that, the little report that Tycho wrote about the supernova explosion. here's a diagram of the constellation Cassiopeia, and in it appeared this object I, which he says is Nova Stella. This is an object that had not been seen before. It was visible for the better part of a year in 1572, and then it faded away. If we look at that same location in the sky, or what we believe is the same location in the sky, because Tycho gave us roughly where to look, then this is what you see in X-rays nowadays. So if you point a telescope that is sensitive to X-rays at the sky, then this is what you see, and this is basically the exploding, expanding aftermath fireball of the supernova explosion that's still propagating into the gas in between the stars. And you can see that sort of coincidentally, it actually sort of looks like the coronavirus. That was not intentionally, but you can see that the explosion gave rise to all sorts of turbulence in the gas that has been heated by the explosion. We can also, from more detailed studies, find out what different elements are present in this bubble of gas that's being blown back into the gas in between the stars. And we can see how supernova explosions of this particular type, for instance, are the source of most of the iron that is present in our world. So if you have a piece of steel in your hands right now, a lot of that steel was ultimately born in explosions that sort of look like this. So now, so people went out and actually started looking for light echoes in the sky. They looked at locations where dust clouds might be present to see if they could actually see echoes of light slowly propagating, apparently running away from the site of Tycho supernova remnant. So here are two images from a paper I took from Rest et al. In the Astrophysical Journal Letters in 2008, which was one of the first, if not the first, report on this. And here's an image taken of a piece of the sky in 2006, and here's an image of that same piece of the sky taken in 2007, about a year apart. These guys went out and took like hundreds and hundreds of images around the sky over big pieces of the sky, just simply trying to see if they could see changes. So on the lower left right here is an image that was made by subtracting the 2006 image from the 2007 image. And you can see that most of the stars have gone away because they have not changed at all. So if you take the difference, this image minus this image, all of that goes away. Some of the brighter stars are difficult to get it straight, so they put a mask across those very bright stars because otherwise they would obscure they would be very bright features in the image, and we don't want them. And then you can see that there's these streaks that indicate the location of light that appears to have been moved from this image to this image. So when you take the difference between this image and this image, if there's a ridge of light that moved to the lower left over here compared to where it was in this image in 2006, you would see a white band over here. So there's a series of white bands over here that seem to indicate that there's a ridge of light present in the 2007 images that has moved a little to the lower left compared to where it was in 2006. Does that make sense? You can actually see the light running through and being scattered in dust clouds over here and slowly advancing. So then you determine the location of these running light fronts, these echoes, and you put arrows on them, and you have lines that point back to where they came from, and then you find this is only a small section of them, but you look at a series of these images, and they all seem to intersect near Tycho supernova remnant. So it looks like this is light that traveled to this location over here, and then some of it got scattered into our direction from over here. A year later, there's still light traveling in this direction, and is now being scattered from a dust cloud that sits a little further out, or these dust clouds have a finite extent. So the echo will move out a little bit. So you can verify the location of this origin of the light echoes by looking at the intersection of the blue lines. There's only a few here, but if you look at the ensemble of the dozens and dozens of blue lines that these guys have drawn, they do intersect near Tycho supernova remnant. And not only that, there's other supernova remnants in the sky for which this also works. So this actually allows you to see the light from the supernova from 1572, because this is light that has traveled a different way. It's come to us. Tycho, had he had the equipment that we have right now, would have looked at the supernova, and he would have probably tried to, like we would do nowadays, take a spectrum of the supernova to try to determine the nature of the supernova. Is it a type 1 supernova, type 2 supernova? Is it the remnant of a massive star exploding? Or is it in fact a white dwarf star that's being ignited and burns through its heavy elements into iron? But he couldn't do that because there were no spectrometers in 1572, of course. So now there's light that has taken another 448 years, and now it comes to us, but now we have these pieces of equipment. So we can subject the light that has been scattered to things that Tycho could not do to it. And here is the spectrum of the light echo. If you take the faint wisps that I showed you before, you take the spectrum of that light, you pull it apart into the components of different wavelengths, then you get a diagram that looks like this. So this is a diagram that covers colors between roughly the blue and the red. So this is about the range of wavelengths to which your eye is sensitive. And here are three honest to God certified type 1 supernovae, because they were observed directly and the light from those supernovae was studied and they are type 1 supernovae. And here's the light echo from 1572, and it fits precisely the pattern outlined by these other type 1 supernovae. So we can actually see that this was a type 1 supernova, and we can determine how much iron this thing produced and all sorts of stuff. We also know exactly how long ago it happened and stuff like that. So we can study supernova 1572 as if it happened yesterday this way, right? Isn't that weird? This is, like, I think, the only legitimate time travel sort of like situation that I can think of. Not into the future, but at least into the past. Okay, so now this gave rise to the idea that if you pull away the little set of pictures that overlays part of this view graph, Bill had warned me, but anyway, what I wrote down here is the galaxy actually keeps an astronomical archive for us, basically, right? You can go in, you can look at the sky, and you can find light that has been traveling for a while, and it is actually related to interesting phenomena you already know about, or maybe you don't know about. And this light will be around for centuries, possibly. In visual and infrared light, the light from supernova explosions, we will be receiving light from supernovae for centuries after the supernova explosion. So it is as if, we basically have surveillance video running. The galaxy is running surveillance video on what happens inside it. And we now know how to pull the video and look at prior dates. We can see what happened in the past. Now, we can also do this in X-rays, it turns out, not just in visual light, you can also do it in X-rays. X-rays also get scattered by dust particles. But the difference is that X-rays are not easily scattered through angles much larger than a fraction of a degree. And so that limits, in that diagram with the triangle that I showed you, that limits that angle theta on the left-hand side of it. That cannot be very large. It's typically much smaller than it is for visual light. And therefore, we cannot see X-rays scattered with very long time delays, because that would involve very large scattering angles, and that is just unlikely to happen for X-rays. So it turns out, for X-ray sources in the galaxy that have flashes, explosions, and things that go, the scattered light will be present for something up to about a decade or so. So we can see things that have happened in our galaxy up to 1 or 2 decades ago this way. So here's a picture of a fancy picture of what a situation like that might look like. And this is an image made by my former student, Leah Corrales, who's now at the University of Michigan, and her colleague, Sebastian Heinz, at the University of Wisconsin. So they made images of the sky using NASA's Chandra X-ray Observatory satellite superimposed on an HST image. So these stars in the background over here, that's the HST image. But the colored diffuse figures that are superimposed on them are in fact diffuse X-rays from the sky. And so they pointed the telescope at an object in the constellation the Swan. It's called V404 Cygni. It is a very bright source of X-rays. It comprises a normal star and probably a black hole. Gas falls into the black hole. It becomes a very bright source of X-rays. And these things typically undergo outbursts. The process of transferring mass and having it fall into the white dwarf is typically not a steady process. And so when there's been an outburst in brightness from an object like this, that's when we will see this in the scattered light. The halos that represent light that has traveled at different time delays will appear at later times. And so the object itself sits somewhere at the center over here, and you can see these concentric rings, and this is all light that's been scattered that came within a few years of the outburst. The outburst preceded the arrival of this light that's in these rings, if you see what I mean. And because there are different dust clouds along the line of sight, you actually get to see light scattered from discrete clouds and therefore occupying different echoes. You get different echoes from different clouds of gas along the line of sight. So now this principle also works if the source is far beyond the galaxy. The light does not have to be made in the galaxy for this to work. So if you think about the following situation, here's the galaxy seen from the top, let's say. There's dust all over the place. This is the space outside the galaxy. We're in the galaxy somewhere. And there's the source of light that has a flash, a brief flash of light, very, very far away from the galaxy. Here's the light that comes towards us directly. We'll see this light arrive. And then later, we'll see the light that came from the source that was actually scattered through a small angle off the dust particles and came to us, like this. And so this works if you move your little mosaic of phase pictures aside a little bit. I should have put it closer to the center. There are objects that are at very large distances away, cosmic distances away from our own galaxy. They're called gamma ray bursts. The aftermath of gamma ray bursts, typically there's a brief display of about a day of strong X-ray emission, and then the whole thing slowly peters out and goes away. And you can see in the direction of this particular gamma ray burst, that was the gamma ray burst of March 12, 2003, X-ray images of the position of that gamma ray burst show there's still light seen from the direct source, but there's also a halo of scattered light. And you can see, if you look closely, how the halo of the scattered light gets bigger and bigger and bigger, because as the time delays grow longer and longer, we're seeing light that has been scattered through larger and larger angles, so that this piece of the path becomes longer and longer. So we know that the process works. If a source far away from our galaxy undergoes a brief episode of increase in brightness in X-rays, and we look at the direction of that object, even if the object itself is no longer visible, the light that it emitted, some of it will scatter off the dust clouds in our own galaxy, and we will see an echo or a halo, and it will be centered on the location of the original object that underwent the flash of light. And we'll see a small concentric halo extend. Depending on what direction we look at and how much dust there is along the line of sight, how many light years of the line of sight are filled with dust, that delay could be of order just hours to days. If we look directly out of the galactic plane into perpendicular to the galactic plane, perpendicular to the thin dimension of the pancake, basically. But if we look in the plane of the galaxy, then there's 60,000 light years of extent, and the time delays can easily be as large as decades. So now we get to the point. This is what I wanted to do. And this is what we've been working on the last summer. We can use this for finding and locating the counterparts to gravitational wave sources. And you may know about gravitational wave sources. The first one was found on September 14, 2015. The LIGO interferometer experiment announced, together with the LIGO experiment, announced that they had actually seen the first characteristic signal from characteristic signal from two black holes that coalesced, that got so close to each other that they formed a single black hole. In the process of doing this, the geometry of space-time gets distorted, and the ripples, the distortion ripples away from the location of the two black holes in the form of a wave, just much like a water wave. And very, very sensitive equipment, extremely sensitive equipment, can actually see these ripples in the geometry of space-time pass by. So this was the first time humanity had ever seen this. Here's a picture of detection by an instrument in Washington State and another parallel identical instrument in Louisiana. And both at the same time saw a signal that goes like whoop, 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 gone. They saw the same signal to within the errors, and this represents a ripple in the geometry of space-time that has been excited by the coalescence of two black holes at very large distance away from the Earth. So this is something people have been looking for a long time. You also know that this garnered a number of people Nobel Prizes and stuff like that. Here's a fanciful representation of what this might look like if you were close enough that you could actually see sort of, you're not that far away from black holes that you can actually see that there's a piece of the sky that is, you cannot see light coming from behind the black hole. And so this would be the two black holes seen against a very distant background of stars. You would see a characteristic fishbowl-like distortion of the geometry of space-time surrounding the two black holes. If they're close enough to each other, they will fall on top of each other. because they lose energy by emission of gravitational waves from a single black hole, and the ripples that they excite on the geometry of space-time travel like waves at the speed of light. Here's a more fanciful representation of the same thing that NASA put together. This is a so-called artist's impression, and here's something to suggest that there are ripples in the geometry of space-time that are going to be traveling away when these two holes hit each other. Now, the funny thing is that when you look at the signal, over here is time. So you see something go foop, 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 foop. You see a signal of which the amplitude increases over here, and the frequency of the signal also increases. You see that the oscillations become slightly faster towards the end, and this is the time that the two black holes really merged. So now that turns out that signal is unique enough, and it has enough information that the theory of general relativity tells us that we can get the distance to the source of these gravitational waves in meters. This is a very unusual situation. So gravitational wave sources, two black holes falling on top of each other and making a ripple in space-time are a natural standard for the emission of gravitational waves. The change of the frequency of the signal and the way that the amplitude of the signal rises just before the coalescence contains enough information to determine the distance to these objects in meters. And so if we could find where these objects actually were before they coalesced, if we can make a measurement of the size of the universe at the time that the coalescence happened, then we can do cosmology, right? We can use these objects because we know how far away they are from a direct measurement of the properties of the gravitational waves. We would know how far in the past the event happened. If we can combine that with the measurement of the size of the universe at that time, we can then make that plot that we referred to earlier that shows the size of the universe as a function of time, and we can see how the expansion rate of the universe may have changed over time. Now, in order to do this, for the size measurement, for determining what the size of the universe was at the time that the black holes fell on top of each other, you need to know precisely in the sky where the event happened. And because the black holes themselves are black, they don't provide you with the information that you need in this case. If you can find the host galaxy in which the event went off, then we can use the light from the stars in the host galaxy to help us determine what the redshift of the object is, as it's called. And that's a measurement of the size of the universe at the time that the two black holes fell on top of each other in units of the size of the current size of the universe. So in order to pinpoint in which galaxy the event went off, you have to be able to pinpoint the location of the gravitational wave source to a fraction of an arc minute. So this is something that's not often appreciated by people who are not astronomers. The sky is incredibly big and it's full of stuff. And so if somebody tells you that, go find an interesting, unusual object in a region of about 10 by 10 degrees, so 20 times the size of the full moon on the side, that's hopeless. There are so many, there are billions of objects in there. And there's like not a hope in hell that you could simply, from knowing to about 10 degrees, determine which, if any of these objects is an interesting object that may have recently had a black hole coalesce inside it, or it's completely unfeasible. I should also say, if we do find the precise positions of black hole mergers, then we can also do a whole bunch of interesting fundamental physics of black holes. So we can also say interesting things about gravity. We can test the general theory of relativity to higher precision and stuff like that. So it's not just cosmologists who would like to be able to do this. Now, currently, as I said, it's impossible to find the precise location on the sky from gravitational wave data alone. It turns out that the gravitational wave observatories are extremely sensitive. They can see these small ripples in the geometry of space-time, small changes in length of an object to 1 part in 10 to the 21. That's a 1 followed by 21 zeros, right? To quote Philip Morrison. So, but the price that you pay, if you have only one of these observatories or two of them, then you cannot really tell where on the sky the event happened. That is the problem. And so for two events that have happened, we've had about 24 over the last 5 years. For one event in 2015 and another in September 2015, the first one, in fact. Here's a picture of the sky. This is a big piece of the sky. Here's the galactic plane again, and on it is plotted are these sickly shaped bananas, and these bananas enclose regions that we can identify with, let's say, 90 or 99% confidence, enclose the true position of the gravitational wave source. So we can say with, let's say, 99% certainty that it happened somewhere inside this magenta region. We can say with only 10% certainty maybe that it happened within this red region over here, right? So the more precisely you would like to know, the less certainty we have that you've got the right position. Now, as I told you earlier, an area on the sky that is this big is this astronomically hopeless hunting ground. And so that's where the story stops. If there is no other signal to look for, we will not know what the positions of gravitational wave sources are unless we have multiple gravitational wave observatories, and we can do triangulation where a series of these bananas will be intersecting from different observatories, and then we'll get more precise positions. The other thing that's really difficult to do is that that first event I showed you a few graphs ago, one of the most amazing things about this first gravitational wave signal ever seen by humanity is that it wasn't even weak. So what we had all been anticipating was, to be perfectly honest, is that we would be staring at graphs that, if you allow my another auditory rendition of data, that would have looked like this. Noise! And then somebody would have stood up and said, like, well, this looks like noise, but after careful analysis, we've determined that hidden in the noise is actually a highly significant signal. That was what we thought was going to be the first, and that would be most of the events. But it turns out the first one you could actually see on the screen. So this was like one of the most delightful surprises associated with the discovery. It wasn't even marginal. It was so clear that you could just see it. Now, many of these events, that is not the case. And so you may not find a gravitational wave event corresponding to the coalescence of two black holes in data until hours or days or sometimes years after the event. Currently, people are writing papers about the last 5 years of data taken with the gravitational wave observatories, and they're finding with less confidence, they're still finding new events that had not been flagged before. Those are now of order 5 years ago, right? So not only do we not know where they happened, we sometimes don't even know that they happened until years after the events. So how are we going to do physics with that? Well, okay, this is where the speculation comes in. If there is an episode X-ray emission at the time that the two black holes merge, and I'm not just saying this myself, there are people who have written papers about that this is in fact not a crazy idea. Over the last few months, the hunch has grown stronger that in some fraction of gravitational wave events that involve very massive black holes, they do happen in dirty environments with lots of gas, and it's perfectly conceivable that in the process of the merger, there will be an episode of gas falling into one or both of the black holes or the resulting black hole and giving rise to an episode of X-ray emission that might last of order hours to days. So if that happens, right, then the gravitational wave event will be accompanied by a flash of X-rays, basically, that lasts maybe a few days at most. That will be happening in a region that you may know to possibly 10 by 10 degrees or so. And if you're lucky, you know about it within a few hours after it really happened. And so we thought, like, well, in that case, we're going to go and look to see if we can see halos of scattered light in X-rays, right? Because they will be around for at least a day, up to decades after the events. And they will have a highly unusual shape, something that people are currently not looking for. And the center of those shapes will indicate where the event actually happened. And so we simulated some images of what this might look like, knowing what the dust in the interstellar medium looks like, properties of X-ray telescopes. And so with my students, I made some synthetic images, and we post this as a challenge to new group members. And I look at this image and tell us what you see. And oh, wait, oh, yeah, that's right. There's a circle right there. There's a faint halo that we superimposed. This is fake, right? We made this data ourselves. Okay, so the challenge is going to be to look through data that in principle could contain a halo to find something that looks possibly as faint but characteristic as this. And who could have guessed that this summer in a blind search, people actually found something like this? It is not a gravitational wave source, but it very, again, powerfully illustrates the principle. So the Germans and the Russians currently have a satellite experiment up in space. It surveys the entire sky in the course of 6 months. They've released some images from their first 6-month scan of the sky. And in one of those images appears this thing right here, right? It looks exactly like the fake image that we had calculated ourselves. And so this turns out is centered on a faint source that's still visible over here. This is an X-ray binary near the galactic center that had an X-ray outburst 2 years ago, and 2 years after the event, this X-ray survey picked up an echo in the interstellar medium. So this demonstrates the whole idea. If something goes kaboom in X-rays way beyond the galaxy, we'll have a decade to look for this characteristic halo shape. All right, so what we're doing right now is we're actually examining the galactic plane in X-rays. There's a lot of data from 2015, when the first gravitational wave source was detected, to the present. And there's about 10 gravitational wave events that have a finite probability that they may have actually been behind the galactic plane. And so we calculated the probability that we're going to be unlucky and not a single one of those happened to have been behind the galactic plane, because as you can see from a picture like here, you know, the thing may have happened over here or here, but we're calculating, suppose it happened over here, there's only a few % probability that in fact it did happen over here in the galactic plane where we want it, where the echoes will linger. But if you have 10 of them and there's a 5% probability for each of them to have been behind the plane, then you can calculate what is the probability that not a single one will happen behind the plane. Currently, the state of the data is such that the probability that that at least one of these events did in fact go off behind the galactic plane is 18%. So we're looking through all these X-ray images with an 18% chance of success, so to say. And you might say like, that sounds not very good. Okay, let me tell you this. If somebody came up to you and says like, here's 5 lottery tickets, one of these will get you $1 million, right? That's about the Nobel Prize. You would be up for that, would you not? Those are pretty good odds. So in astronomical terms, 20% is actually pretty serious. So besides which, it's just fun to do. Within the next few weeks to months or something, you might suddenly be looking at an image like, oh, what is this? And all right, so I'll end on one of the images that we are currently looking at. So my student Johin made this a few days ago. He stitched together a series of X-ray images of a region in which a gravitational wave source may have gone off in 2019 in April. And so we were looking at this like, what do you think, dude? I think, I don't know. Did you see anything? Well, maybe this over here. Johin has, maybe this over here. Johin has figured out a very clever way that was actually first suggested by the particle physicists for finding patterns in images like this, and that's what we're going to be running on all of those. So if this works, I promise you I'll be back next year, and I'll say, more fun with dust or something like that, and then we can maybe talk about having identified the first counterpart to gravitational wave sources. Thank you for your attention and your patience.